that these can be, well, this happened earlier. It just didn't. Referred to. One of the more common ways is by calling it a tangent line approximation. So if you can keep that in mind, instead of a linear, we could think of it as a tangent line approximation. And then we'll talk about something called differentials, which are very much related to, I almost said indefinite integrals. That wouldn't have been good. Implicit differentiation. It's all the I words were running around in my head. Okay. And so we'll take a look at that. Linear approximations, more than differentials, will be seen on the AP exam. And like I said, they normally will say, what is the tangent line approximation? We'll take a look at it, and I think it'll make pretty good sense as we go through. So for a linear approximation, we're going to use a tangent line at some point a f of a to approximate the values of our function f of x when x is near a. The equation of the tangent line is y equals f of a plus f prime of a times x minus a, which is exactly the point slope form of the tangent line, just moving that y value to the other side of the equation. The further we get x from a, the less accurate our approximation becomes. And we'll also take a look at how we can figure out how close we need to be, depending upon the function. So we can use that approximation and we can say our actual function is pretty darn close to our tangent line approximation or linear approximation. And so basically we're taking our function and transforming it into a linear function. And that linear function is called the linearization of f, specifically at a. All right, so find the linearization of f of x is equal to the square root of x plus 3. And here we're saying at a equals 1, so we're given our value for a. And use that to find the approximate value of the square root of 3.98 and the square root of 4.05. And I know what many of you are probably thinking, oh, Mr. Gingrich, why don't I just use my calculator? Because I said don't. We'll see. We'll actually compare the approximations to the actual calculated values. I shouldn't say actual because your calculator is going to estimate because it's an irrational number. So we need to find the derivative. What is the derivative of x plus 3 to the 1/2? Should go to the video and make one of my distant learners to answer that one. Oh, you should see all the smiles out here from the group.
It's 1/2 x plus 3 to the -1.
Okay, remember, this is, even though it doesn't look like it, this is a chain rule. We do bring the power down, take x plus 3 to 1 less power, and then take the derivative of x plus 3, which is just 1. So we often don't even consider that as a chain rule problem. That is exactly right. All right. What else do we need to know? F of a. So when I plug 1 in to my function, the two hardest questions you're going to get today, 1 plus 3. All right, and the square root of 4? 2. So this would be 1 plus 3 to the 1/2, which is 2. And then f prime of a. Now for that one, I might rewrite my derivative without negative exponents, or you could use your calculator and use the negative exponents. Just remember, this would be 1 over 2 times 1 plus 3 to the 1/2. And how much is that? One-fourth. Good. I heard someone mumble it, I'm sure. Either that or I'm hearing things and, it really doesn't matter to me. So our formula says that our function is approximately equal to the linearization, and that linearization or linear approximation is going to be f of a plus f prime at a times x minus a. Now we want to figure out these two approximate values. So a couple of things to be mindful of. We're going to plug in x into our linear approximation. So x, in this case, we're going to add 3 to it. And when we add 3 to it, our first approximation gives us 3.98. So what value does x have? Don't say 3.98. 0.98, right? It's what would we plug in here to make the inside equal to 3.98? All right, so you just want to be careful of that in your homework. If you have x plus something or x minus something that you're thinking about, okay, what value does x have to have? So we're going to take the linear approximation of 0.98. And I think 1.995. But someone's going to, I'm sure, check me on that. Yeah, we're getting a nod on the check, like it. Okay. So a couple of things. I hope that we can see that this is probably a pretty good approximation, right? The square root of 3.98 should be a little bit less than 2. Okay. If I would have plugged in 3.98 here, we've gotten a number way bigger than 2. So, use a little bit of, problem solving. Hey, does that seem like a good approximation? And hopefully that'll, hopefully you have the problem solving skills to do that. Now, I just want to check. Yeah, I know my screen sharing is paused. It's okay. If I actually calculate what that square root is. Okay, interesting. Let's try that again. So if I just did the square root of 3.98. So not bad. I mean, if I round to 3 decimal places, it's exactly the same as the approximated value our calculator gives. All right, then we were asked, well, let's try 4.05. So again, thinking about our original function, what value would x have so that I'm taking the square root of 4.05? 1.05, excellent. All right, so if I, again, calculate that, 2 plus 1/4 times 0.05, I believe that would give me 2.05. 0.01225. Yes, no, maybe so. Okay. And again, if we just check, hey, how close are we? Again, rounding to 4 decimal places, we're right on, which is nice. The further we get away from 3, the more likely we are to get a different value. So I should say 4. The further we get away from a square root of 4, the further a gets away from 1. All right. So one question that might be fun to answer, it's actually fun to ask and then watch you guys struggle to answer it. But for what values of x is the linear approximation accurate to within 0.5? And so we did something real similar. To this. So we want to know when our linear approximation is within half of the actual. Well, the actual function is x plus 3 to the 1/2. So for our lower end of our approximation, we would subtract the 0.5. And for the upper end of our approximation, we would add 0.5. And we could do some algebra and get the x's all by themselves, and really more work than we need to do, because hopefully we have that graphing tool, and we can graph these 3 functions and find their point of intersection. So that's the way I would go about it. So I am going to graph x plus 3. No, don't do that. There we go. To the 1/2. And I could put so I could use the square root symbol as well. I'm just typing it the exact same way that I've written it. 2 plus 1/4 x minus 1. And x plus 3 to the 0.5 plus 0.5. I'm afraid to graph it. No, I'm not. I'm going to zoom out just a little bit. That was more than I wanted to zoom out, but hopefully on the previous screen, and I'm going to zoom in, so there. So you can see, I hope, that our actual, our linear approximation, our red graph, intersects the black graph twice. It doesn't intersect the blue graph, and that's okay. So now we just need to figure out the x values for those points of intersection. And again, I think we've talked about this already, I think, right? Yeah, okay. So option 5. Come on, there we go. There are my 2 graphs. And here you want to be careful of your point of intersection. Now, obviously, I need to be closer to this one than to this one for the first point of intersection. AP Calculus says, hey, let's round that to 3 decimal places, negative 2.657 roughly. And then we can find the other point of intersection by repeating the process. All right, I'm going to assume that's close enough. All right, so the error message, no sign change, just means, hey, they don't intersect. Just means my window isn't set up to go wide enough. So I'm pretty sure that they'll cross there. And there we see 8.657. 8.657. All right. Differentials. So differential in the case of a function that is y equals a function of x is the dy part. And it is defined in terms of dx by the equation dy equals f prime of x dx. The biggest use for a differential is to estimate error in measurements, or to estimate the maximum error that our measurement has without having to make a bunch of calculations. I know for, for part of your assignment, it's just going to be find dy if x equals this and dx equals this. So just plugging in and solving for dy. So kind of straightforward stuff. And then there'll be a couple of examples where you're asked to estimate the error. And we'll do an example like that. Not terribly difficult. But it'd be good practice. All right. So the error in a given measurement will be the value we plug into dx in our differential equation. All right, so here we go. The radius of a sphere was measured and found to be 21 centimeters with a possible error of 0.05 centimeters. What is the maximum error in using this value of the radius to compute the volume of the sphere? I'm telling you, do not calculate the radius or the volume with the given radius and then with the radius 0.05 less than and 0.05 greater than. No, let's use calculus. Let's be a little bit more academic about it. So the first thing we should probably know is, I'll give you time to write before the first thing we need to know is. Formula for the volume of a sphere. Excellent. And yes, those formulas, if you need them on the AP exam, would be given. So let's find the differential, which really says, hey, let's take the derivative with just a little bit. It's almost like an implicit differentiation, right? So we take the derivative of v, and we just call that dv. That's going to be our maximum error on volume. Four-thirds and pi are just constants, so we don't have to worry about them for the derivative. They're just going to kind of follow along. And then the derivative of r cubed would be 3r squared dr. For a differential, you're going to have d of the variable on the left and d of the variable on the right. The 3's do cancel there. So if I just rewrite interesting thing about the derivative of volume of a sphere, 4 pi r squared is the formula for the surface area of a sphere. That's kind of interesting. All right. Maybe I'm the only one that found it interesting. I don't know. I don't care either. You know. So if we plug in our measured radius and the error in our radius, that calculation will tell us the maximum, a good estimate of the maximum possible error in the volume. So again, I would use my calculating tools. Four times pi times 21 squared times 0.05. So the good news is we're within 277.088 cubic centimeters. I'm just going to wait because I know someone's going to double check my work and say, Gingrich, you're off by, no, good. So my question to you is, how accurate is that? Is that good? Is that bad? Should we be worried? You think what? It seems kind of bad. Well, let's see how bad it is. So one thing that we can do is we can check the relative error, which would be taking the error that we calculated and dividing by the total volume. And that would be true for any relative error. Take the calculated error divided by the calculated total. So our error was 4 pi r squared dr. And our actual volume was 4/3 pi r cubed. So a couple of things reduce out. Pi reduces out. 2 of the r's reduce with 2 of the r's, leaving us with just r to the first. The 4 and the 4 reduce out. So the relative error in this case, I'm going to take the 3 that's in the denominator of the denominator and move it up to the numerator. Right? 1 over 1/3 is the same as 3. And you're just so excited you dropped your pen. So 3 times 0.05 divided by 21. So the relative error is 0.007. Okay. Again, how accurate is that? Well, what if we think about that as a percentage? That would be 0.7%. So we're off by less than 1%. Not too bad. So that initial large error is actually within 1% of the actual calculation. It's kind of nice. I think I already double checked, but I'm going to triple check that the page numbers are correct. Page numbers look good. I'll give you, I don't know, 15, 20 minutes to work, and then I will put up the review assignment as well. What's that?
Includes corrections.
Yep, quiz corrections can go in the bin, just move the stapler. So, one thing on the review assignment, problem 76 talks about a rectangular window surmounted by a semicircular window or a semicircular pane of glass. So in the past, there have been students who didn't understand what that meant. So for 76, what's happening is you have a rectangular window and a semicircle above it, like so. Just want to make sure that we're clear on the language there. Onliners, have a wonderful rest of your Tuesday. Unless you have a question. Yeah, sure. Couldn't get out of there fast enough, I guess.